There is a kind of wind that moves across empty places at night, carrying nothing, touching no one, a motion so faint it exists at the edge of what can be felt rather than heard. The air holds a particular coldness then, not the sharp cold of winter, but something older, something that speaks of distance and the long hours when the world turns away from the sun. In that darkness, beneath a sky scattered with ancient light, the ground beneath us feels solid, final, as if it were the deepest thing we could ever know. We stand on continents and sense their weight, their permanence, and when we think of depth, we imagine it extending downward from where we stand, into rock and heat and the compressed history of stone. We think of mines that burrow into mountains, of caves that open like wounds in the earth, of valleys carved so deep that light reaches their floors only briefly, if at all. This is where depth lives in our minds, in the places we can walk to, the places we have named and mapped and sometimes descended into with ropes and lights, and the stubborn certainty that the deepest parts of the world must be beneath our feet. But there is a question that sits quietly in the spaces between what we assume and what is true. A question that asks us to reconsider where the surface of the planet actually ends and where its true depths begin. If you find yourself drawn to such questions, to the places where intuition meets the patient correction of reality, then you might consider subscribing to Quiet Science, where we explore these quiet inversions together, slowly, without urgency. Because the answer to where the planet reaches its deepest point is not where most of us would think to look. It is not in the heart of a continent or at the bottom of a canyon carved through ancient rock. The deepest part of the planet is not on land at all. When we think of going deep into the earth, we think first of the places where the land itself has opened, where gravity and time and the patient work of water have carved passages into the continental bedrock. We think of caves that extend beneath mountains, of limestone passages where rivers once flowed, and where now only darkness pools in chambers no sunlight has ever touched. There are caves in the Caucasus Mountains where spelunkers have descended for days, rappelling down shafts and squeezing through gaps in the rock, going deeper and deeper until they reach depths of more than 2 kilometers below the surface, where the air is different and the silence has a weight that presses against the ears. These are the deepest natural penetrations into the continents, the places where the solid ground has been hollowed out by the slow chemistry of groundwater dissolving rock over millions of years. Standing at the entrance to such a cave, looking down into the dark, it is easy to believe you are looking toward the deepest part of the world, that if you followed that passage far enough, you would reach some final floor, some ultimate bottom where the earth itself begins. But caves are passive spaces, voids created by subtraction, by the removal of material rather than the presence of an abyss. The rock around them remains, solid and ancient, and the caves themselves are merely interruptions in that solidity, pockets of emptiness that go only as far as water and time have been able to carve them. Deeper still are the places where humans have gone with intention, with machines and explosives, and the determination to see what lies beneath the surface of the continents we inhabit. Gold mines in South Africa descend nearly 4 kilometers into the earth, following veins of precious metal that formed billions of years ago when the planet was younger and its geology more violent. The miners who work at those depths travel in elevators for nearly an hour to reach the rock face, descending into heat and pressure and a darkness that has never known daylight, where the temperature of the surrounding rock can reach 50 degrees Celsius and must be cooled artificially to allow human survival. These are among the deepest places any person has ever stood, and they represent the practical limit of how far we can burrow into the continents, how deep we can go before the earth itself pushes back with heat and pressure and the sheer cost of moving rock. Even deeper than the mines are the boreholes, the narrow shafts drilled by scientists seeking to understand the structure of the continental crust. The deepest of these, drilled on the Kola Peninsula in Russia over the course of 2 decades, reached a depth of just over 12 kilometers before the project was abandoned, not because the drill had reached any fundamental boundary, but because the temperature at that depth, exceeding 180 degrees Celsius, made further drilling impractical. 12 kilometers into the earth, and yet still within the uppermost layer of the continental crust, still nowhere near the mantle that lies beneath, still in rock that is geologically young compared to the planet's true depths. The Kola borehole is often cited as humanity's deepest penetration into the solid earth, a record that speaks both to our curiosity and to our limitations, to the fact that even with all our technology, we can barely scratch the surface of the planet we call home. And yet these depths, impressive as they are measured from the surface of the land, from the continents that rise above sea level and give us the ground beneath our feet. When we speak of the deepest cave, or the deepest mine, or the deepest borehole, we are speaking of depth relative to a starting point that is already elevated, already lifted above the baseline of the planet's surface. The continents are not the surface, not really. They are platforms, vast rafts of lighter rock floating on the denser material beneath, risen masses that stand above the true floor of the Earth like tables rising from a room. And if we want to understand where the planet truly reaches its deepest point, we have to stop thinking of depth as something measured from where we happen to be standing, and start thinking of it as a measure of distance from some more fundamental reference, some true baseline against which all elevations and depressions should be judged. There are valleys on land that seem to approach this kind of depth, canyons carved by rivers that have spent millions of years cutting through uplifted plateaus. The Grand Canyon in Arizona descends more than 1.5 kilometers below the rim, exposing layers of rock that span nearly 2 billion years of Earth's history, each stratum a chapter in the long story of sedimentation and uplift and erosion. But even the Grand Canyon, vast as it is, begins from an elevation already more than 2 kilometers above sea level, so its floor, though deep relative to its surroundings, is still high above the true surface of the planet. In Tibet, in the eastern reaches of the Himalayas, there is a canyon carved by the Yarlung Tsangpo River that is deeper still, plunging more than 5 kilometers from rim to river in some places, a vertical distance that exceeds even the tallest mountains if measured from base to peak. But again, the starting point is elevated, the rim of the canyon standing at altitudes where the air is thin and the horizon stretches across the roof of the world. These are the deepest valleys on Earth, and they are magnificent in their scale. But they are not the deepest parts of the planet, because the continents, for all their mass and history, are anomalies in the geography of Earth. They cover less than 30% of the planet's surface, and they rise above the surrounding terrain not because they are fundamental, but because they are made of rock that is less dense, more buoyant, able to float higher on the viscous mantle below. The rest of the planet, the majority of its surface, is covered by water, by oceans that hide the true topography of the Earth beneath a layer of moving liquid that reflects the sky and gives the impression of flatness, of a surface that is level and featureless. But beneath that water, beneath the waves and the storms and the sunlight that penetrates only the uppermost layer, the ocean floor stretches away into distances and depths that make even the deepest continental valleys seem shallow by comparison. And it is there, beneath the oceans, that the planet reveals its true extremes of depth, the places where the surface of the Earth falls away, not into valleys measured in kilometers, but into abysses measured in the kind of numbers that challenge the intuition, that make the mind pause and recalibrate its sense of what deep actually means. The ocean appears flat from the shore, a horizontal expanse that meets the sky at a line so distant it curves with the planet itself. We think of it as a surface, as the top of something, and in our minds the depth beneath that surface is an afterthought, a space filled with water, and therefore somehow less significant than the solid depths of continents. But this is an inversion of the truth, a misunderstanding born from the fact that we are creatures of the land, and we measure the world from where we stand. Mountains impress us because they rise above us, because we can see them towering into the sky, their peaks catching the light long after the valleys have fallen into shadow. Mount Everest stands more than 8 kilometers above sea level, and we call it the highest point on Earth, and we are correct in that designation. But height and depth are not opposites in the way we imagine them to be. They are both measurements of displacement from a reference point, and the reference point we use, sea level, is arbitrary in the sense that it represents not the true surface of the planet, but merely the average position of the ocean's surface, a line that shifts with tides and currents and the gravitational pull of the moon. If we could drain the oceans, if we could remove all the water and see the Earth as it truly is beneath that liquid veil, we would discover a landscape far more dramatic than anything visible on the continents. The ocean floor is not a bowl, not a simple depression that gently slopes away from the land. It is a vast and varied terrain of plains and mountains, of ridges and valleys, of features that dwarf the topography we know. And most importantly, it reaches depths that have no equivalent on land, places where the solid surface of the planet descends not just below sea level, but below the deepest valleys, below the deepest mines, below anything we can access by standing on a continent and looking down. The deepest point in any ocean is deeper than the highest mountain is tall, and this asymmetry, this imbalance in the planet's topography, tells us something fundamental about how the Earth is structured, about why the continents rise and the ocean basins fall, and where the true extremes of the planet's surface can be found. Mountains exist because of forces that push rock upward, because of the collision of tectonic plates and the compression of the crust and the slow uplift that can raise seabeds kilometers into the sky over millions of years. But mountains are not simply piles of rock balanced on the surface. They have roots, extensions of the continental crust that reach down into the mantle beneath, supporting the visible peaks, the way the bulk of an iceberg supports the small portion that floats above water. This is the principle of isostasy, the idea that the Earth's crust floats on the denser, more fluid mantle below it, and that anything rising above the surface must be balanced by a corresponding mass extending below. The Himalayas, the tallest mountain range on Earth, have roots that extend as much as 70 kilometers into the mantle, far deeper than the mountains are tall, necessary to support the weight of all that elevated rock. So when we look at a mountain, we are seeing only a fraction of its true structure, only the part that happens to protrude above the surface we have chosen as our reference point. But the ocean floor has no such roots. It is not buoyant. It is made of basalt, of rock that is denser than the granitic rock of the continents, rock that forms at mid-ocean ridges where magma wells up from the mantle and solidifies and then slowly spreads away, creating new ocean floor in a process that has been ongoing for hundreds of millions of years. This denser rock does not float as high as the continents. It sits lower in the mantle, and the result is that the ocean basins are not elevated platforms but depressions, true low points in the planet's solid surface. And because they are depressions, because they sit lower than the continents, they can be filled with water, with the vast volume of liquid that has accumulated on Earth over geological time, condensed from the atmosphere and delivered by comets and volcanic outgassing and the long chemical evolution of the planet. The water fills the basins to a depth that averages nearly 4 kilometers, and that depth is not a measure of how much water there is, but a measure of how low the ocean floor truly sits relative to the elevated continents. From the shore, the ocean extends outward as a nearly level plain, and for the first few kilometers offshore beneath that water, the seafloor does indeed slope gently downward in what is called the continental shelf, a submerged extension of the continent that remains relatively shallow, rarely more than 200 meters deep. This is the familiar part of the ocean, the part where sunlight still reaches the bottom, and where life is abundant, and where the geology is still fundamentally continental, still part of the same granitic platform that forms the land. But the continental shelf is narrow and it does not extend far. Somewhere between 10 and 100 kilometers from the shore, depending on the coastline, the shelf ends abruptly at the continental slope, and the seafloor begins to fall away in earnest, dropping down through the water column toward the abyssal plains that lie below. This is the edge of the familiar world, the boundary between the shallow continental margins and the true ocean basins, and crossing it is like stepping off a cliff into a vastness that has no equivalent on land. The continental slope is steep, descending at angles that can exceed 10 degrees, which does not sound dramatic until you realize that it continues for kilometers, that it represents a fall from the sunlit shelf to the dark plains of the abyss, a vertical drop of 3 or 4 kilometers in a horizontal distance that can be measured in tens of kilometers. If you were to walk down such a slope on land, it would take hours, and you would feel the air grow thinner and colder as you descended, feel the weight of the distance in your legs and lungs. But in the ocean, the descent is through water, through a medium that grows darker and colder and denser with every meter, until at the base of the slope you arrive at the abyssal plains, at the true floor of the ocean basins, at depths where the pressure is measured in hundreds of atmospheres, and where the temperature hovers just a few degrees above freezing, and where the darkness is so complete that no trace of sunlight has ever reached and never will. And yet even the abyssal plains, vast and deep as they are not the deepest parts of the ocean. They are the floor, but the floor is not level. It is interrupted by features, by ridges and seamounts, and in certain places by trenches, by narrow fractures in the ocean floor where the crust is being pulled downward into the mantle, where the seafloor is not simply low but actively descending, creating depths that go far beyond the typical 4 kilometers of the abyss, and into territory that represents the true extremes of the planet's topography. The abyssal plains stretch across the ocean basins like the floors of vast halls, flat expanses of sediment that have accumulated over millions of years as the debris of life and geology settles slowly through the water column and comes to rest in the deep. These plains cover more of the Earth's surface than all the continents combined, lying at depths of 4 to 6 kilometers below sea level, places where the pressure is so great that it would compress a human body instantly, where the cold is absolute and unchanging, where the silence is broken only by the occasional creak of settling sediment or the distant rumble of underwater earthquakes. To reach these depths is to reach a kind of baseline for the planet, a level where most of the ocean floor sits, stable and ancient and far removed from the turbulence of the surface world. But baseline is not the same as bottom, and the abyssal plains, for all their remoteness and depth, are interrupted by features that go deeper still, by places where the seafloor does not simply rest at its usual depth, but actively descends, pulled downward by forces that operate on geological timescales, and that reshape the planet with a patience that makes human history seem like a single breath. These places are called trenches, and they are among the most dramatic features in the topography of Earth, though they are invisible from the surface and were unknown to science until the 20th century, when echo-sounding technology allowed ships to map the ocean floor with sufficient precision to detect them. A trench is not a crack or a fissure in the usual sense. It is a long, narrow depression in the seafloor, typically thousands of kilometers in length, but only 100 or so kilometers wide, carved not by erosion or the collapse of the crust, but by the deliberate motion of tectonic plates, by the process called subduction, in which one plate of the Earth's crust slides beneath another and descends into the mantle below. The ocean floor is not static. It is constantly being created at mid-ocean ridges, where magma rises and solidifies, and it is constantly being destroyed at subduction zones where it bends downward and returns to the depths from which it came. This is the engine of plate tectonics, the slow recycling of the Earth's crust that drives continental drift and volcanic activity and the building of mountain ranges, and it happens at the trenches, in these narrow zones where the seafloor curves downward and disappears beneath the edge of another plate. The process is slow beyond comprehension, measured in centimeters per year, but it has been ongoing for billions of years, and it shapes the planet in ways that are fundamental to its geology. Where a trench forms, the descending plate pulls the seafloor downward with it, creating a depression that can reach depths far greater than the typical abyssal plain. The walls of a trench are steep, often approaching vertical, and the floor of a trench is narrow, a thin ribbon of the deepest seafloor squeezed between the descending plate and the plate that rides above it. These are geologically active places, sites of frequent earthquakes as the plates grind against each other, sites where the stress of subduction is released in sudden motions that can be felt thousands of kilometers away. But they are also places of profound stillness, because the water at these depths is so dense and the current so weak that nothing disturbs the sediment except the occasional tremor, and the trench floor accumulates a record of time that is measured in layers so thin they represent centuries of deposition. There are more than 20 major trenches scattered around the edges of the ocean basins, most of them in the Pacific, where the ocean floor is old and dense and eager to subduct beneath the lighter continental plates or the younger oceanic plates that surround it. The Peru-Chile Trench runs along the western coast of South America, a depression that reaches depths of more than 8 kilometers below sea level, deeper than Mount Everest is tall, a fact that is often stated but rarely felt because the trench is hidden beneath water and we cannot see it or stand at its edge and look down. The Japan Trench lies off the eastern coast of Japan, another subduction zone where the Pacific Plate descends beneath the Eurasian Plate, creating earthquakes and tsunamis and a depression in the seafloor that reaches similar depths. The Tonga Trench in the South Pacific, the Kuril-Kamchatka Trench in the Northwest Pacific, the Puerto Rico Trench in the Atlantic. Each of these is a place where the ocean floor descends to depths that exceed anything found on land, depths that represent the true low points of the planet's solid surface. But among all the trenches, there is one that goes deeper than the others, one where the combination of subduction rate and plate age and geological history has created a depression that reaches the absolute extreme of depth on Earth. This trench lies in the Western Pacific, east of the Philippines and south of Japan, in a region where the Pacific Plate, the largest tectonic plate on the planet, is being subducted beneath the smaller Philippine Sea Plate. The trench is shaped like a crescent, curving through the ocean for more than 2,500 kilometers, but it is only 70 kilometers wide on average, a narrow scar in the seafloor that would be easy to miss if you were flying over it, if the water were transparent and you could see the topography below. But the water is not transparent, and the trench is not easy to reach, and for most of human history it was unknown, a feature so remote and so deep that it existed beyond the reach of our technology and our imagination. The deepest point in this trench, the deepest point in all the oceans, the deepest point on the solid surface of the Earth, lies at a location that has been measured and remeasured with increasing precision over the decades as our instruments have improved. The exact depth varies slightly depending on which survey you consult, because the seafloor is not perfectly smooth and because different measurement techniques give slightly different results, but the consensus is clear. This point lies nearly 11 kilometers below sea level, a depth so extreme that it challenges the mind to grasp it. 11 kilometers is not a number that means much in isolation, but when you consider that it is nearly 3 times the depth of the typical abyssal plain, when you consider that it is deeper than the tallest mountain is tall, when you consider that it represents the vertical distance from the surface of the ocean to a place where the pressure is more than 1,000 times what it is at sea level, the scale begins to register, slowly, like a weight settling onto the mind. This is the Mariana Trench, and its deepest point is called the Challenger Deep, named after the research vessel that first measured its depth in 1951, and it is here, in this remote and narrow depression in the seafloor of the Western Pacific, that the planet reaches its greatest extreme of depth, the point farthest below sea level, the true bottom of the world. The Challenger Deep is not a place anyone goes by accident. It is not on the way to anywhere, not a landmark visible from passing ships, not a feature marked on navigation charts except as a point of scientific interest and a warning of extreme depth. It sits in the middle of the Pacific Ocean, hundreds of kilometers from the nearest land, beneath waters that are themselves thousands of meters deep before you even begin to approach the trench. To reach it requires deliberate effort, requires traveling across open ocean to coordinates that mean nothing to the eye but everything to instruments, requires descending through water column after water column of increasing pressure and darkness until you arrive at a place that feels less like a location on Earth and more like a conceptual extreme, a mathematical limit made physical. The depth of the Challenger Deep has been measured many times since that first sounding in 1951, and each measurement has refined our understanding of just how deep this place truly is. Early measurements using simple echo sounding gave figures around 10,900 meters, depths that were astonishing but imprecise, limited by the technology of the time and the difficulty of measuring vertical distance through thousands of meters of water with varying density and temperature. Later surveys using more sophisticated sonar, using multiple beams that could map not just a single point, but the shape of the seafloor around it, confirmed that the deepest point lies at approximately 10,984 meters below sea level, though some surveys have recorded depths slightly greater, approaching 11,000 meters. The uncertainty is not large, a few tens of meters at most, but at these depths even small uncertainties represent vast volumes of water, vast distances that are difficult to comprehend from the surface. To say that something is 11 kilometers deep is to recite a number, But numbers alone do not convey what depth actually means. If you stood at sea level and looked down into the Challenger Deep, if the water were somehow made transparent and you could see all the way to the bottom, you would be looking at a vertical distance greater than the cruising altitude of most commercial aircraft. 11 kilometers is the height at which planes fly across continents, the altitude where the air is thin and cold and the curvature of the Earth becomes visible. But instead of looking up at that distance, you would be looking down into a column of water so tall that if you dropped a stone from the surface, it would take more than an hour to reach the bottom, falling through the water at a steady rate, slowing slightly as the density increased but never stopping, never encountering anything but water and darkness and the gradual accumulation of pressure that would compress the stone itself, changing its volume imperceptibly but measurably by the time it reached the trench floor. Pressure is perhaps the most immediate reality of depth, the most tangible consequence of being so far below the surface. At sea level, the atmosphere exerts a pressure of approximately 100,000 pascals, a force that we do not notice because we have evolved to live within it, because our bodies are structured to balance that pressure from within. But water is far denser than air, and the pressure increases rapidly with depth, adding another atmosphere of pressure for every 10 meters of descent. At 100 meters depth, a depth that experienced divers can reach with proper training and equipment, the pressure is already 10 times what it is at the surface, enough to compress the air in your lungs to a fraction of its usual volume, enough to make breathing difficult, and to force nitrogen into your bloodstream where it can cause narcosis and decompression sickness if you ascend too quickly. At 1,000 meters, the pressure is 100 atmospheres, and the physiological effects would be lethal to any human without protection. At the depth of the Challenger Deep, the pressure exceeds 1,100 atmospheres, a force so immense that it is difficult to express in terms that feel intuitive. Imagine a column of lead, solid metal, stacked 1,100 meters high, and imagine that column resting on a single square centimeter of surface. That is the pressure at the bottom of the Challenger Deep, a weight of more than 1,000 kilograms, pressing down on every square centimeter of the seafloor, on every surface, on every object that finds itself in that environment. It is a pressure that would crush a human body instantly, that would collapse a submarine not specifically designed to withstand it, that would compress foam and wood and any material with trapped air until the air was forced out and the material itself was reduced to a fraction of its original volume. Styrofoam cups brought to the deep ocean in mesh bags, as experiments returned to the surface, shrunken to the size of thimbles, their structure intact, but their volume reduced by the sheer force of the water pressing in from all sides. Steel spheres thick enough to contain air at 1 atmosphere at the surface would need walls several centimeters thick to avoid being crushed at the depth of the Challenger Deep, and even then, the metal would deform slightly under the load, bending inward in ways that are invisible but measurable, proof that even the strongest materials we can forge are not immune to the weight of all that water. And yet, despite this pressure, despite the cold that hovers just above freezing, and the darkness that is absolute and unbroken by any natural light, the Challenger Deep is not empty. It is not a sterile place. When the first crude descent to the bottom of the trench was made in 1960, when Jacques Picard and Don Walsh climbed into the bathyscaphe Trieste and spent nearly 5 hours descending through the water column to reach the deepest point, they reported seeing a flatfish swimming along the bottom, a sighting that was dismissed by some scientists as unlikely, but that has since been supported by more recent explorations. Life exists at the bottom of the Challenger Deep, not in abundance, but in forms that have adapted to conditions that would seem impossible to any surface-dwelling organism. There are amphipods, small crustaceans that look like oversized shrimp, that have been collected from the trench floor, their bodies adapted to the pressure not by being stronger, but by eliminating air entirely, by filling themselves with incompressible fluids and soft tissues that cannot be crushed because there is nothing in them to compress. There are microbes that live in the sediment, feeding on the organic matter that drifts down from the surface world, processing it in chemical cycles that are slow and efficient and perfectly suited to an environment where energy is scarce and time is not a limiting factor. The existence of life at such depths is a reminder that what seems extreme to us is merely the normal environment for organisms that have had millions of years to adapt, that the boundaries we perceive are often boundaries of our own physiology and technology rather than boundaries of possibility itself. The Challenger Deep is the deepest point on Earth, but it is not a void. It is a place with its own geology and biology and chemistry, a place that participates in the systems of the planet even as it remains almost entirely isolated from the surface, connected to the upper world only by the slow rain of particles that fall through the water and by the currents that move across the abyssal plains and into the trench, bringing with them the faint echoes of processes happening thousands of kilometers away and thousands of meters above. The darkness at the bottom of the Challenger Deep is not the darkness of a moonless night or the darkness of a cave deep underground. It is a darkness that has never been interrupted, a darkness that predates human existence and will outlast it, a darkness so complete that the concept of light becomes abstract, theoretical, something that belongs to a different realm entirely. Sunlight penetrates seawater to depths of only about 1,000 meters under the best conditions, in the clearest tropical waters, where the sun is directly overhead and the water is free of particles that scatter and absorb the light. But even in these ideal circumstances, the light that reaches 1,000 meters is faint, a dim blue glow that carries almost no energy and illuminates almost nothing, just enough to register on sensitive instruments, but not enough to support photosynthesis, not enough to create shadows or reveal shapes. Below 1,000 meters, there is no sunlight at all, no trace of the surface world's daily cycle of day and night, no variation in illumination except for the occasional bioluminescence of passing organisms, brief flashes of chemical light that serve as signals or lures or warnings, in a world where vision has adapted to detect the faintest glimmers. At the depth of the Challenger Deep, even bioluminescence is rare, because the organisms that produce it are scarce, and the energy required to generate light is a luxury that few can afford in an environment where food arrives only as a slow rain of detritus from above. The darkness here is not punctuated by flashes. It is unbroken, absolute, a condition that has persisted for as long as the trench has existed, for tens of millions of years at least, since the Pacific Plate began its descent beneath the Philippine Sea Plate and created this depression in the seafloor. The sediment that covers the floor of the trench has never been touched by light, never been warmed by the sun, never been part of any cycle that involves photosynthesis or the daily rhythms of surface life. It is sediment that formed in darkness, and settled in darkness and will remain in darkness, a record of time accumulated in a place where time itself seems to move differently, where the processes that govern change operate on scales that make the human lifespan invisible. If you were to descend to the Challenger Deep in a submersible, protected from the pressure and the cold by a sphere of thick steel or titanium or ceramic composite, you would experience this darkness not as an absence, but as a presence, as something that presses against the viewports and swallows the light from your vessel's lamps as soon as it leaves the source. The lamps would illuminate a small sphere around you, a bubble of visibility that extends perhaps 10 or 20 meters, depending on the power of the lights and the clarity of the water, but beyond that sphere, there would be nothing, no gradient of fading light, no hint of what lies just out of reach. The darkness at these depths does not permit your eyes to adjust to it. There is nothing to adjust to. Without artificial light, you would see nothing, not shapes or shadows or the faintest suggestion of forms, just a blackness so total that it feels like a physical barrier, like a wall that your vision cannot penetrate, no matter how long you wait or how intently you try to perceive. And in that darkness, in that absence of visual information, the other qualities of the deep become more apparent, more pressing. The cold, for instance, which at the bottom of the Challenger Deep hovers between 1 and 4 degrees Celsius, just above the freezing point of seawater, kept from freezing by the salt content and the pressure, but still cold enough that it would numb exposed skin within seconds and induce hypothermia within minutes if you were unprotected. This is the temperature of the abyssal ocean everywhere, a cold that is not seasonal, not variable, not something that changes with the time of day or the weather at the surface. It is the baseline temperature of deep water the temperature to which all water in the ocean eventually settles as it cools at the poles and sinks and spreads across the seafloor, carrying with it the cold of polar winters and distributing it throughout the ocean basins. The water at the bottom of the Challenger Deep may have last been at the surface hundreds or thousands of years ago in the North Atlantic or the Southern Ocean, and it has traveled through the deep ocean circulation, the slow overturning of water masses that connects the surface and the abyss on timescales that are measured in centuries. But perhaps the most striking quality of the Challenger Deep, more even than the darkness or the cold, is the silence. Sound travels well through water, better than it does through air, and the ocean is filled with noises, with the calls of whales and the clicks of dolphins and the crackling of shrimp and the low-frequency rumble of ships and storms and geological activity. But at the bottom of the trench, in the deepest part of the ocean, these sounds are muted and distant, filtered by thousands of meters of water that absorb the higher frequencies and leave only the lowest, the sounds that can travel great distances, but that carry little information, little sense of their origin. The clicks of a sperm whale hunting squid at 2,000 meters depth might reach the Challenger Deep as a faint tapping, a rhythm without context. The breaking of waves at the surface, the collision of water and air that creates a constant background noise in the shallow ocean, does not penetrate to the trench floor. The sound of the surface world is filtered out entirely, leaving only the deep sounds, the groans of the Earth's crust as plates shift and stress is released, the occasional rumble of an earthquake miles away, the subtle creaking of the seafloor as it settles under its own weight. If you listened, if you had instruments sensitive enough to detect the faintest vibrations, you would hear the trench itself, the slow grinding of the Pacific Plate as it descends into the mantle, a process that happens continuously, but so gradually that it is imperceptible on human timescales. Millimeters per year adding up over millions of years to create the depression you are sitting in. You might hear the movement of sediment, the rare avalanche on the steep walls of the trench, triggered by an earthquake or the accumulation of too much weight, a cascade of particles tumbling down the slope and coming to rest on the floor, adding another layer to the record of time. You might hear the faint biological sounds, the movements of amphipods crawling through the sediment, or the contraction of muscles in some unseen organism, sounds so quiet they would be inaudible anywhere else, but here, in this silence, they register as events, as proof that something is happening, that the deep is not frozen in stasis but is participating, in its own slow way, in the ongoing processes of the planet. But mostly what you would hear is nothing, or rather, you would hear the absence of the familiar sounds that define the surface world, the absence of wind and waves and voices and engines, the absence of the acoustic clutter that fills our environment and that we tune out without thinking. In the Challenger Deep, there is no clutter to tune out. There is only the rare event, the occasional sound that breaks the silence and then fades, leaving you once again in a quiet so profound that it becomes a kind of presence itself, a quality of the environment as fundamental as the pressure or the darkness or the cold. The organisms that live at the bottom of the Challenger Deep do not experience their environment as hostile. They have no memory of surface conditions, no reference point against which to measure the pressure, or the cold, or the darkness. For them, 1,100 atmospheres is simply the normal state of existence, the pressure at which their proteins fold correctly, and their cell membranes maintain their integrity, and their biochemical reactions proceed at the rates necessary for life. The cold water is not an obstacle but a constant, a temperature that slows their metabolism, but also reduces their energy requirements, allowing them to survive on the sparse food that reaches them from above. The darkness is not an absence, but the default condition, and the organisms that live here have either lost their eyes entirely, having no use for organs that detect light that never arrives, or they have evolved eyes so sensitive that they can detect the faintest bioluminescence, the rare flashes of light produced by other organisms that serve as the only visual signals in an otherwise black world. These adaptations are not remarkable in the sense of being unusual or exotic, though they appear that way to us. They are simply the solutions that evolution has found to the problems posed by this particular environment, solutions that have been refined over millions of years through the same processes of variation and selection that operate everywhere else on the planet. The amphipods that crawl through the sediment of the Challenger Deep, for instance, have bodies that are soft and flexible, lacking the rigid exoskeletons that their shallow water relatives possess, because rigidity is a liability under pressure and flexibility allows them to compress slightly without being damaged. Their cells contain osmolytes, small organic molecules that help stabilize proteins and prevent them from denaturing under the extreme conditions, molecules that are produced metabolically and maintained at concentrations that balance the external pressure. These amphipods feed on whatever organic matter settles into the trench, on the bodies of dead organisms that fall from the surface or the mid-water, on the fecal pellets of animals that live higher in the water column, on the fragments of algae and plankton that somehow make it through thousands of meters of water without being consumed by the organisms living at intermediate depths. The food supply at the bottom of the ocean is limited and unpredictable, arriving not in a steady stream, but in pulses, in events that might happen once a year or once a decade, like the fall of a whale carcass or the bloom of surface plankton that produces enough excess material to create a significant rain of particles. When food does arrive, the deep-sea organisms respond slowly, their metabolism too sluggish to allow rapid feeding, their movements deliberate and economical, conserving energy because the next meal is uncertain and might be a long time coming. There are fish in the trench, snailfish that have been recorded at depths exceeding 8,000 meters, their bodies gelatinous and almost transparent, their bones reduced to cartilage because calcium carbonate, the material that makes bones rigid, becomes soluble under high pressure and cannot be maintained without expending energy that these fish cannot afford to waste. These snailfish are predators, feeding on amphipods and other small invertebrates, but they are not active hunters. They move slowly through the water, drifting more than swimming, conserving energy and waiting for prey to come within reach, rather than chasing it actively. The deepest fish ever recorded was found at a depth of more than 8,000 meters in the Mariana Trench, a depth that represents the practical limit for fish as a group, not because the pressure at greater depths is lethal, but because the biochemistry of fish bodies cannot function below a certain pressure threshold. The protein TMAO, trimethylamine N-oxide, which deep-sea fish use to stabilize their proteins and counteract the effects of pressure, reaches a concentration limit beyond which it begins to interfere with other cellular processes, and this limit corresponds roughly to depths of 8,000 to 8,500 meters. Below that depth, fish cannot exist, not because they lack the adaptations, but because the adaptations themselves become problematic, because the solutions to the pressure problem create new problems that cannot be solved within the constraints of fish physiology. But other organisms, invertebrates that do not rely on the same biochemical strategies, can and do exist at greater depths, all the way to the bottom of the Challenger Deep, where amphipods and sea cucumbers and microbes continue to live and feed and reproduce in their slow, patient way. The sea cucumbers that have been observed on the floor of the Challenger Deep are perhaps the most visible of the large organisms, though visible is a relative term in a place where nothing can be seen without artificial light. They are detritivores, crawling across the sediment and processing it through their digestive systems, extracting whatever organic material remains in the particles that have settled there and excreting the inorganic fraction back onto the seafloor. Their movements are so slow that they are difficult to detect in real time, but time-lapse photography from remotely operated vehicles reveals that they do move, that they are actively feeding, that they are not simply passive lumps of tissue, but functioning organisms engaged in the same basic activities as their shallow water relatives, just at a pace that is adjusted to the energy constraints of the deep. A sea cucumber might take an hour to move a meter, might spend days in a single location processing the sediment beneath it, might live for decades or longer, its slow metabolism extending its lifespan far beyond what would be typical for similar organisms in warmer, more productive environments. The microbes in the sediment, invisible to the naked eye and detectable only through chemical analysis and DNA sequencing, are perhaps the most abundant and the most important organisms in the trench, because they are the ones that complete the decomposition of organic matter, breaking down the complex molecules that fall from above into simpler compounds that can be used by other organisms or that simply dissolve into the water and become part of the chemical cycles of the ocean. These microbes are not unique to the deep ocean. Many of them are related to species found in other environments, in soils and freshwater and shallow marine sediments, but they have adapted to the conditions of the trench in ways that are subtle and difficult to study, requiring laboratory experiments conducted under high pressure to understand how their enzymes function and how their metabolic pathways differ from those of their shallow water relatives. What is clear is that they are active, that they are processing organic matter and releasing nutrients, that they are participating in the carbon cycle and the nitrogen cycle and the sulfur cycle, that they are, in their quiet way, as essential to the functioning of the deep ocean as the more visible organisms that swim or crawl across the seafloor. And yet for all this activity, for all the life that exists at the bottom of the Challenger Deep, the overwhelming impression is one of emptiness, of vast spaces inhabited by only a few individuals, of an ecosystem that operates at a density so low that encounters between organisms are rare events rather than common occurrences. The biomass of the deep ocean is a tiny fraction of the biomass of the surface ocean, and the biomass of the Huddle Zone, the depths below 6,000 meters where trenches are found, is a tiny fraction of the biomass of the abyssal plains. Life persists here not because the environment is hospitable in any conventional sense, but because life, once established, is remarkably difficult to eliminate entirely, because there will always be organisms that can find a way to extract energy from even the most marginal environments, that can slow their metabolism and extend their lifespans, and wait patiently for the rare influx of resources that makes growth and reproduction possible. The sediment that covers the floor of the Challenger Deep is not deep in the sense that we usually understand the word. It is not a thick accumulation of material that has built up over eons, not a layered archive of geological history stretching back through millions of years. In most parts of the ocean, in the abyssal plains where the seafloor is stable and undisturbed, sediment accumulates at rates measured in millimeters per 1,000 years, building up slowly as particles fall from the water column above, as the shells of dead plankton and the dust blown from continents and the remnants of volcanic eruptions settle gently onto the seafloor and compress under their own weight into layers that preserve a record of oceanic conditions stretching back tens of millions of years. But the floor of the Challenger Deep is not stable. It is being actively subducted, dragged downward into the mantle along with the Pacific plate that it sits upon, and this motion, though slow by any human measure, is fast enough on geological timescales that sediment does not have time to accumulate to any great thickness before it is carried away into the depths of the earth and destroyed. The sediment layer at the bottom of the trench is thin, perhaps only a few hundred meters at most, and even this represents only a fraction of the total history of the trench, because the oldest sediment has already been subducted, already been pulled beneath the overriding plate, and subjected to pressures and temperatures that transform it into metamorphic rock or melt it entirely and recycle it back into the mantle. What remains on the surface is recent sediment, geologically speaking, material that has fallen from the water column within the last few million years and that will itself be subducted eventually in another few million years, leaving no trace except for the tiny fraction that might be scraped off and accreted onto the edge of the overriding plate, incorporated into the geology of island arcs or continental margins, preserved as a thin layer of ocean floor rock embedded in what will eventually become mountains. This impermanence is characteristic of ocean floor everywhere, not just in trenches. The seafloor is young compared to the continents because it is constantly being created at mid-ocean ridges and destroyed at subduction zones, recycled through the mantle, in a process that takes roughly 200 million years from creation to destruction. The oldest ocean floor currently in existence is found in the western Pacific, far from any mid-ocean ridge, and it is approximately 180 million years old, dating to the Jurassic period when dinosaurs walked the continents and the Atlantic Ocean was just beginning to open. But even this ancient seafloor is young compared to continental rocks, some of which are more than 4 billion years old, dating back to the earliest era of Earth's history when the planet was still cooling from its formation and the first stable crust was beginning to solidify. The continents persist because they are buoyant, because they float on the mantle and resist subduction, but the ocean floor is dense and it sinks, and its fate is always to be recycled, to be returned to the depths and remelted, and eventually brought back to the surface as new magma at a mid-ocean ridge, completing a cycle that has been operating for as long as plate tectonics has existed on Earth. The subduction of the Pacific plate beneath the Philippine Sea plate that creates the Mariana Trench is happening now continuously at a rate of approximately 5 centimeters per year, about the rate at which fingernails grow. This is not a metaphor or an approximation. It is the actual rate, measured by GPS stations on the islands near the trench, and by the analysis of earthquake patterns, and by the spacing of volcanic islands in the Mariana Arc, all of which confirm that the Pacific plate is descending steadily and predictably into the mantle. 5 centimeters per year does not sound like much, but it adds up. Over 1 million years, the plate descends 50 kilometers, far enough to reach depths where the rock begins to melt and release water and generate the magma that feeds the volcanoes of the island arc. Over 10 million years, the plate descends 500 kilometers, deep into the mantle where it becomes indistinguishable from the surrounding material, its identity as a former piece of ocean floor lost entirely, transformed into just another part of the convecting mantle that slowly circulates through the Earth's interior. The earthquakes that occur along the subduction zone at the Mariana Trench are evidence of this ongoing motion, sudden releases of stress that build up as the descending plate grinds against the overriding plate. Most of these earthquakes are small, too small to be felt at the surface, detectable only by seismometers that record the faint vibrations traveling through the Earth's crust. But occasionally the stress builds to a level that can only be released in a major earthquake, a rupture that propagates along the fault zone for tens or hundreds of kilometers, releasing energy equivalent to millions of tons of explosives and generating seismic waves that travel around the planet multiple times before dissipating. These large earthquakes are rare, happening perhaps once every few decades or centuries along any given section of a subduction zone, but they are inevitable, a consequence of the fact that the motion of tectonic plates is continuous, but the friction between plates is not constant, building up until it exceeds the strength of the rock, and then releasing suddenly in a motion that might last only seconds, but that represents the culmination of decades or centuries of slow, imperceptible stress. Accumulation. And yet even these earthquakes, violent as they are simply part of the normal operation of the planet, events that would happen with or without human observation, part of the slow work of plate tectonics that reshapes the surface of the Earth on timescales that make the entire span of human history seem like a brief flicker. The Mariana Trench itself is temporary, not in the sense that it will disappear tomorrow or next year, but in the sense that it exists only as long as the Pacific plate continues to subduct beneath the Philippine Sea plate, and eventually, perhaps in tens of millions of years, the configuration of plates will change, the subduction will cease or shift to a new location, and the trench will fill in or be uplifted, or simply cease to be the deepest point on the planet. Ocean basins open and close, continents drift and collide, mountain ranges rise and erode, and through all of this, the deep ocean floor records and erases its own history in a continuous cycle that has no beginning and no end, only the ongoing present of geological process. The organisms living at the bottom of the Challenger Deep are part of this continuity, inhabiting a place that is ancient in human terms, but young in geological terms, a place that has existed for only a few million years and that will eventually be destroyed along with the seafloor it sits upon. They are not aware of this, of course. They do not know that the ground beneath them is moving, descending, carrying them toward eventual destruction in the mantle. They live in the present, in the only time frame that matters for living things, the time frame of individual lifespans and reproductive cycles, and the availability of food. But they are also part of a larger pattern, part of the way life responds to and inhabits every available niche, even niches that are temporary on geological timescales, even niches that will eventually disappear as the planet continues its slow transformation. There is something humbling in this realization, in the understanding that even the deepest, most extreme, most seemingly permanent features of the planet are transient when viewed on the timescales that the Earth operates on, that the Challenger Deep, for all its immensity and its record-breaking depth, is just a momentary depression in the surface of a planet that is constantly recreating itself, constantly recycling its materials, constantly erasing its own history and writing new chapters. In rock and water, and the slow motion of continents across the face of the globe, only a handful of human beings have ever descended to the bottom of the Challenger Deep, a number so small that it is often compared accurately to the number of people who have walked on the moon. The comparison is apt not just numerically, but experientially, because both represent journeys to places that are profoundly alien, profoundly difficult to reach, profoundly inhospitable to human life without extensive technological protection. But there is a difference in the nature of the remoteness. The moon is distant in the literal sense, hundreds of thousands of kilometers away across the vacuum of space. But once you reach it, the surface is accessible, visible, open to exploration within the limits of your life support system. The Challenger Deep is only 11 kilometers away, a distance you could walk in a few hours on level ground. But those 11 kilometers are vertical, through water that grows denser and darker and colder with every meter, and the journey takes hours not because of the distance, but because of the medium you must pass through and the pressure you must withstand when you arrive. The first descent to the Challenger Deep was made in 1960 by Jacques Piccard and Don Walsh in the bathyscaphe Trieste, a vessel that looks less like a submarine and more like an underwater balloon, with a large float filled with gasoline for buoyancy and a small steel sphere attached beneath it to hold the two occupants. The sphere was less than 2 meters in diameter, barely large enough for 2 people to sit in a cramped space surrounded by walls of steel more than 12 centimeters thick. Steel chosen not for its strength alone, but for its ability to resist the pressure that would be exerted at depth, pressure that would compress the sphere slightly, elastically, causing the metal to flex and groan, but not, if the engineers had calculated correctly, to rupture. The descent took nearly 5 hours, a slow fall through the water column, as the bathyscaphe released ballast and allowed gravity to pull it downward, passing through the sunlit surface waters and into the twilight zone, and then into the midnight zone, and finally into the Hadal zone, the region below 6,000 meters where trenches are found, and where the names for depth run out and must be borrowed from mythology, from Hades, the ancient Greek underworld. When Trieste reached the bottom, when the sphere touched down on the sediment of the Challenger Deep, and the 2 men inside looked out through the small viewports, they saw what they later described as a flat, featureless plain of sediment, illuminated by the lights of the bathyscaphe in a circle of visibility that extended only a few meters before being swallowed by the darkness. They stayed on the bottom for only 20 minutes, barely enough time to take photographs and make observations, before beginning the ascent, releasing the ballast that held them down and allowing the buoyancy of the gasoline-filled float to carry them back toward the surface. The entire mission lasted more than 8 hours, and when they emerged they had proven that it was possible for humans to reach the deepest point on Earth, that the technology existed to protect fragile human bodies from pressures that would otherwise crush them instantly, but they had also demonstrated how difficult and dangerous such a journey was, how much time and effort and risk was required to spend 20 minutes at the bottom of the ocean. For more than 50 years after that first descent, no one returned to the Challenger Deep. Not because the achievement was considered complete, not because there was nothing more to learn, but because the technology required was expensive and complex, and the number of institutions capable of building and operating such vehicles was small, and because the scientific community's attention was directed elsewhere, toward more accessible depths, toward regions of the ocean that could be explored more easily and more frequently with remotely operated vehicles and autonomous instruments. The Challenger Deep remained, in a sense, unexplored, a place that had been visited once but not studied, a location on maps but not a place integrated into the ongoing work of oceanography. It was known to be there, known to be deep, but its ecology and geology and chemistry remained largely mysterious, inferred from studies of other trenches and other deep-sea environments, but not directly observed or measured. The next crewed descent came in 2012, when filmmaker James Cameron descended alone in the submersible deep-sea Challenger, a vehicle he had commissioned specifically for the purpose of reaching and filming the deepest parts of the ocean. Cameron spent several hours at the bottom, longer than Pickard and Walsh had been able to, and he collected samples of sediment and water and brought back high-definition video footage of the trench floor, images that revealed a landscape similar to what Trieste had seen 50 years earlier, a flat expanse of sediment with occasional amphipods and other small organisms visible in the lights of the submersible. The images were detailed and scientifically valuable, but they also reinforced the impression of emptiness, of a place where life existed, but in such sparse concentrations that the overwhelming experience was one of absence, of vast spaces with very little in them, of an environment that supported life but did not encourage it, that allowed organisms to persist at the very edge of what metabolism and adaptation could achieve. Since then, a few more descents have been made, each adding incrementally to our understanding of the trench, each confirming that life exists at these depths and that the environment is not as sterile or as hostile as early theories suggested, but also each reminding us how difficult it is to study a place that requires hours of travel time each way, and that can be visited only by vehicles that cost millions of dollars to build and operate, and that carry significant risks every time they dive. The total amount of time that human beings have spent at the bottom of the Challenger Deep, adding up all the crude descents ever made, is measured in hours, perhaps 10 or 12 hours total, a span of time shorter than a single working day, spread across more than 6 decades. For context, astronauts have spent more than 600 days on the surface of the Moon during the Apollo missions alone, and the International Space Station has been continuously occupied for more than 2 decades, meaning that human beings have spent literally years in space, in an environment that is in many ways more hostile and more remote than the deep ocean, but that is also more accessible in the sense that once you have built the infrastructure to get there, you can stay and work, and live for extended periods. The contrast reveals something about the nature of ocean exploration, about the fact that depth is a kind of remoteness that is difficult to overcome, not because of distance, but because of the physical properties of the medium, because water at high pressure is an environment that resists human presence in ways that vacuum does not, because maintaining a vessel at 11,000 meters depth requires constantly fighting against forces that want to collapse the vessel, whereas maintaining a station in orbit requires only balancing the gravitational pull of Earth against the forward momentum of the station, a balance that, once achieved, persists without continuous effort. The deep ocean is not a place we can colonize or inhabit, or even visit frequently with current technology. It is a place we can glimpse briefly, at great expense and with great effort. And then we must leave, returning to the surface where the pressure is bearable, and the light is abundant, and the resources we need to survive are available. Most of what we know about the Challenger Deep comes not from crude descents but from remotely operated vehicles, from cameras and instruments lowered on cables or propelled by their own motors, machines that can stay longer and go more frequently because they do not carry the burden of keeping humans alive. These vehicles descend through the same water column, experience the same increasing pressure and decreasing temperature, but they do so without the psychological weight of human presence, without the knowledge that 2 people are sitting inside a metal sphere, hoping that the calculations were correct, and the welds are sound and the viewport seals will hold. A remotely operated vehicle is expendable in a way that a crude submersible is not, and this changes the nature of what can be attempted, the risks that can be taken, the places that can be explored. If a remotely operated vehicle fails at depth, if the pressure hull cracks or the electronics short out or the tether breaks, the loss is measured in dollars and time and perhaps some irreplaceable instruments, but not in lives. This difference is not trivial. It is the reason why the deep ocean, despite being closer than space, has been explored less thoroughly, because the technology required to protect human life at depth is more complex and more expensive than the technology required to protect human life in space, and because the ocean itself is an active environment, filled with water that corrodes and conducts electricity and exerts pressure from all sides, whereas space is passive, empty, a void that does not push back. The remotely operated vehicles that have visited the Challenger Deep in recent years have revealed details that crewed missions could not capture, simply by virtue of being able to stay longer and move more freely without the constraints of life support and the psychological burden of human occupants. They have recorded hours of video footage showing the sediment surface, the tracks left by organisms moving across it, the burrows and mounds that suggest biological activity beneath the surface. They have collected samples of sediment and water that have been analyzed in laboratories on the surface, revealing the chemical composition of the trench floor, the isotopic signatures that indicate where the organic matter comes from and how old it is, the genetic material that identifies which species are present, and how they are related to organisms found in other parts of the ocean. They have measured temperature and salinity, and dissolved oxygen, confirming that the water at the bottom of the trench is not stagnant, but slowly circulating, connected to the broader deep ocean by currents that move at speeds measured in millimeters per second, but that are sufficient over years and decades to exchange the water in the trench with water from the surrounding abyss. These measurements and observations have built a picture of the Challenger Deep as a place that is extreme but not unique, a place that shares many characteristics with other Hadal zones, with the floors of other trenches in the Pacific and Atlantic and Indian Oceans, places that are all deep and cold and dark and under immense pressure, but that are also all connected by water and by the biology that has adapted to these conditions. The organisms found in the Challenger Deep are not entirely unique to that location. Many of them, or closely related species, are found in other trenches, suggesting that there is some degree of connectivity, some mechanism by which organisms can move between trenches, or by which their larvae can be transported by currents across the abyssal plains that separate one trench from another. This connectivity is surprising given the isolation of each trench, given that the trenches are separated by thousands of kilometers of seafloor that is not at Hadal depths and that represents a different environment with different pressures and different biological communities. But life finds ways to cross barriers, to colonize distant habitats, and the Hadal zones, though extreme, are not closed systems. They are part of the larger ocean, part of the global ecosystem, and the organisms that live in them are part of lineages that extend back through time and across space, connected by evolution and by the slow movement of water and nutrients through the ocean basins. But for all this connectivity, for all the ways in which the Challenger Deep is similar to other Hadal zones and part of the broader deep ocean ecosystem, it remains the deepest point, the place where the numbers reach their maximum, where the pressure is highest and the depth is greatest and the distance from the surface is furthest. This distinction is not arbitrary. It means something, not in terms of the biology necessarily, because the organisms at the bottom of the Challenger Deep are not significantly different from organisms at the bottom of trenches that are a few hundred meters shallower, but in terms of what the place represents, the conceptual extreme, the answer to the question of where the planet goes deepest. And that answer is not on land, it is not in a cave or a mine or a borehole drilled into a continent. It is beneath the ocean, beneath thousands of meters of water, in a place that most people will never see and that exists, for most of us, only as a point on a map, as a set of coordinates, as a depth measurement that is difficult to comprehend and that requires comparison to other things, to mountains and airplanes and the height of buildings, in order to make any kind of intuitive sense. There is a particular quality to extreme places, a quality that is hard to articulate, but that is felt when you think about them for long enough. They mark boundaries, not boundaries that prevent crossing, but boundaries that define the limits of what is possible within certain constraints. The Challenger Deep is the deepest point on Earth, but it is not the deepest point imaginable. There are moons in the solar system with oceans beneath their ice that may be much deeper, with water layers tens or hundreds of kilometers thick, with floors that lie farther below their surfaces than the Challenger Deep lies below ours. There are theoretical limits to how deep an ocean can be on a rocky planet, limits set by the pressure at which water stops being a liquid and becomes a high-pressure ice even at temperatures far above freezing, or by the pressure at which the rocky mantle beneath the ocean begins to flow and adjust to the weight of the water above it. The Challenger Deep is the deepest point on our planet, but it is not the deepest point in the universe, and this distinction matters because it reminds us that the extremes we observe are always contingent, always specific to the particular conditions of the place we are observing, and that there are always other places, other scales, other extremes that we have not yet encountered or imagined. But within the context of Earth, Within the planet we inhabit and the environment we have evolved to understand, the Challenger Deep represents a true limit, a place where you cannot go deeper without leaving the planet entirely, a place where the solid surface of the Earth reaches its maximum distance below sea level and where the ocean reaches its maximum depth. This is not a limit that matters to the organisms living there. They do not know they are at the bottom of the world. They know only their immediate environment, the sediment beneath them and the water above them, and the sparse food that sustains them. But for us, for beings who think in terms of maps and measurements and records, the Challenger Deep matters precisely because it is an extreme. Because it answers a question that humans seem compelled to ask, the question of where the limits are, where the highest point is, and where the lowest point is, and what lies at those extremes. The surface of the ocean is where we encounter it, where our boats float, and where the light reflects off the waves, and where the temperature changes with the seasons and the weather. It is the interface between water and air, the boundary we cross when we dive beneath or when we stand on the shore and look out toward the horizon, and it feels, from our perspective, like the most important part of the ocean, the part that affects us directly, the part that matters for navigation and fishing and climate, and all the ways the ocean intersects with human life. But the surface is only a skin, a boundary layer measured in meters or tens of meters, where the water is mixed by wind and waves, and where sunlight penetrates, and where temperature varies with the time of day and the season. Below that surface, the ocean extends downward for an average depth of more than 3.5 kilometers, a volume so vast that if you could remove all the water from the ocean basins and spread it evenly over the entire planet, it would cover the Earth to a depth of more than 2.5 kilometers, drowning every mountain and continent beneath a global ocean with no land visible anywhere. A water world, like some of the moons we have discovered orbiting distant planets in other solar systems. We do not think of Earth as a water world because we live on land, because the continents are where we build our cities and grow our food and conduct our lives. But from the perspective of surface area, the planet is mostly ocean, nearly 71% covered by water. And from the perspective of topography, the planet is mostly deep ocean, with the majority of the seafloor lying at abyssal depths far below the reach of sunlight or the influence of surface processes. The continents are outliers, elevated platforms that rise above the baseline, and we happen to be creatures adapted to live on those platforms, on the small fraction of the planet's surface that is both solid and above water. But the solid surface of Earth extends far beyond the edges of the continents, continues beneath the water, drops down through continental shelves and slopes into abyssal plains and trenches. And it is this submerged surface, this hidden topography, that represents the true extent of the planet's solid exterior. The continents are islands in a sense, not just geographically but topographically, elevated regions surrounded by lower terrain, and the fact that the lower terrain is covered by water does not make it less real or less significant, only less visible to us. This inversion of perspective, this recognition that the baseline of the planet is not the surface of the continents, but the floor of the ocean basins, changes the way we think about depth and height, about what it means for something to be deep or shallow. When we say that the Challenger Deep is nearly 11 kilometers deep, we are measuring from sea level, from the average position of the ocean's surface, and this is a reasonable reference point because sea level is relatively constant and easy to define and serves as a common baseline for measuring both elevation and depth. But sea level is not a feature of the solid Earth. It is a feature of the water that covers the Earth, and it exists at the height it does because of the volume of water in the oceans and the capacity of the ocean basins to hold that water. If the ocean basins were deeper, if the seafloor sat lower in the mantle, sea level would be lower as well, and the continents would rise even higher above the water. If the ocean basins were shallower, sea level would be higher, and the continents would be partially or entirely submerged, their highest peaks forming archipelagos in a shallow global sea. The depth of the ocean basins and the height of the continents are both consequences of the same underlying geology, of the fact that the Earth's crust comes in two types: continental crust made of lighter rocks that float high on the mantle, and oceanic crust made of denser rocks that sit low, and of the fact that these two types of crust are constantly being created and destroyed and rearranged by the motion of tectonic plates. The continents are old, with some rocks dating back billions of years, because continental crust resists subduction and accumulates over time. But the ocean floor is young, with the oldest oceanic crust being less than 200 million years old, because oceanic crust is constantly being recycled, created at mid-ocean ridges and destroyed at subduction zones. This difference in age reflects a fundamental difference in stability, in permanence, and it means that the features of the ocean floor, including the Challenger Deep, are transient in a way that the continents are not, present for only a few tens of millions of years before being carried away and replaced by new seafloor formed elsewhere. But transient does not mean insignificant, and the fact that the Challenger Deep will eventually be subducted and destroyed does not diminish its present reality or its status as the deepest point on the planet. It is deep now, in the present, and it has been deep for several million years already, and it will remain deep for several million years more, a span of time that encompasses the entire history of the human species and far exceeds the duration of any human civilization or institution. On the timescales that matter to us, to living organisms and human societies, the Challenger Deep is as permanent as anything on Earth, as stable as the mountains or the continents themselves, and its depth is a fact that will not change within any time frame that is meaningful to our individual lives or our collective memory. And yet there is something humbling in knowing that even this extreme, even this record-breaking depth, is temporary on geological timescales, that the planet is constantly reshaping itself, and that the features we observe and measure and marvel at are only the current configuration of a surface that has been different in the past and will be different in the future. The Mariana Trench did not exist 100 million years ago. The Challenger Deep did not exist 50 million years ago. They came into being as the Pacific Plate began to subduct beneath the Philippine Sea Plate, and they have been growing deeper and longer as that subduction has continued, but eventually the subduction will cease or shift to a new location, and the trench will fill in or be uplifted or simply cease to exist in its current form. Other trenches will form elsewhere, perhaps deeper than the Challenger Deep, perhaps not, and the title of deepest point on Earth will pass to a new location, to a place that does not yet exist, to a depression that will form millions of years from now when some other plate begins to subduct beneath some other plate in some other part of the ocean. This knowledge does not make the Challenger Deep any less impressive or any less deep, but it does place it in context, reminds us that the Earth is not a static object but a dynamic system, constantly changing, constantly rearranging its surface features, constantly creating and destroying the topography that we observe and study. And it reminds us that the measurements we make, the records we keep, the extremes we identify are all snapshots of a moment in geological time, accurate for now but not eternal, true for the present configuration of the planet but not representative of the planet as it was or as it will be. The Challenger. Deep is the deepest point on Earth today, but it is not the deepest point the Earth has ever had or will ever have, and this distinction, subtle as it may seem, is important because it reinforces the idea that the planet operates on timescales that dwarf our own, that the features we think of as permanent are merely long-lasting from our perspective, and that the story of Earth is still being written, still unfolding, with chapters yet to come that we cannot predict or imagine. There is a difference between knowing that a place exists and understanding what that existence means, between being able to point to coordinates on a map and being able to grasp the reality of what those coordinates represent. The Challenger. Deep exists at 11 degrees north latitude and 142 degrees east longitude, numbers that can be entered into any GPS device or mapping software, numbers that will produce a point on a screen showing a location in the western Pacific Ocean, thousands of kilometers from the nearest major city, hundreds of kilometers from the nearest inhabited island. But these numbers, precise as they are, tell you nothing about what it is like to be in that place, nothing about the pressure or the darkness or the cold, nothing about the silence or the emptiness or the slow motion of organisms across sediment that has never been touched by light. Coordinates are abstract, a way of organizing space on a grid, a system for navigation and reference, but they are not experiential. They do not convey the weight of 11,000 meters of water above you, or the compression of that water into a density that is noticeably greater than the water at the surface, or the way that pressure changes the properties of materials, making some things more rigid and others more flexible, changing the chemistry of seawater so that gases dissolve differently and minerals precipitate or remain in solution under conditions that would not occur at shallower depths. To understand a place like the Challenger, deep requires more than knowledge of its location or its depth. It requires some sense of scale, some comparison that allows the mind to bridge the gap between the abstract number and the physical reality. 11 kilometers is not a distance we experience regularly in the vertical dimension. We experience horizontal distances of 11 kilometers easily, driving them in minutes or walking them in a few hours, but vertical distances of that magnitude are rare in human experience. Commercial aircraft fly at altitudes between 10 and 12 kilometers, so 11 kilometers is roughly the height at which you would be flying across a continent, looking down at the ground far below, seeing the landscape reduced to patterns of fields and roads and rivers, seeing cities as clusters of structures too small to resolve individually. But in an airplane, you are moving horizontally more than vertically, and the altitude is something you register intellectually by looking at instruments or by noting the thinness of the air rather than something you feel directly in your body. The vertical dimension at those heights is an abstraction, a number on a display, not a tangible experience of climbing or descending. The Challenger deep inverts this, takes that same vertical distance and extends it downward instead of upward, and in doing so creates an experience that is fundamentally different from flight because water is not air, because descending through water means fighting against increasing pressure and decreasing light, means moving through a medium that becomes denser and more resistant with every meter, means entering an environment that is not passive like the atmosphere, but active, pressing in, from all sides filling every space, testing every seal and joint and weld for weakness. And unlike the atmosphere, which thins with altitude and eventually gives way to the vacuum of space, water does not thin with depth. It compresses slightly, becoming denser, but it remains water all the way down, remaining liquid at temperatures that would freeze it at the surface, remaining a continuous medium that supports life and chemistry and the slow circulation of currents, never transitioning to some other state or giving way to emptiness. The Challenger Deep is at the bottom of 11 kilometers of water, but it is not at the bottom of the ocean in the sense of being at the edge of something, at a boundary beyond which there is nothing. It is simply at the lowest point within a system that extends in all directions, connected by water to the surface and to the abyssal plains and to every other part of the ocean, isolated by distance and depth, but not by any fundamental barrier. This connectivity is important because it means that the Challenger Deep is not a separate world, but part of the same planetary system that includes the surface ocean and the atmosphere and the continents, part of the same cycles of water and carbon and nutrients that operate everywhere on Earth, just operating more slowly, more subtly, with longer timescales and smaller fluxes. The organic matter that falls into the trench from above originates at the surface, produced by photosynthetic organisms that use sunlight to convert carbon dioxide and water into organic compounds. And when those organisms die or are eaten, their remains sink slowly through thousands of meters of water, being consumed and decomposed and fragmented along the way until only a small fraction reaches the trench floor. But that fraction is still a connection, still a flow of energy and material. From the sunlit world to the dark world, a link that sustains the deep-sea communities and makes it possible for life to exist in places where no light reaches and where local production of organic matter is impossible. The water itself circulates, though slowly, and the water at the bottom of the Challenger Deep was once at the surface, somewhere, decades or centuries ago, before it cooled and sank and began its long journey through the deep ocean, carrying with it dissolved gases and nutrients and the chemical signature of the place where it last contacted the atmosphere. This water will eventually return to the surface, brought up by upwelling currents in regions where deep water rises to replace surface water that has been pushed away by winds, completing a cycle that takes hundreds or thousands of years, but that connects every part of the ocean to every other part, ensuring that the deep is not stagnant or isolated, but is part of a global circulation that mixes and redistributes the properties of seawater on timescales that are long by human measures, but relatively fast by geological measures. And yet, despite this connectivity, despite the physical and chemical links between the Challenger Deep and the rest of the ocean, the deep remains profoundly isolated in experiential terms, in the sense that it is a place that cannot be casually visited or frequently studied, a place that requires enormous effort and resources to access, and that reveals its secrets slowly, grudgingly, through measurements and samples and brief observations that must be pieced together into a coherent picture. Over years and decades of research, the isolation is not absolute, but it is effective, and it means that the Challenger Deep exists for most people only as an idea, as a fact learned from books or documentaries, as a record in a database of extreme places, but not as a place that can be experienced or visited or incorporated into the everyday understanding of the world. It is too far away, not in the horizontal sense, but in the vertical sense, too deep to reach without technology that is rare and expensive, too extreme in its conditions to support human presence without extensive life support, too dark and cold and pressurized to feel familiar, or welcoming or safe. This remoteness is part of what makes the Challenger Deep significant, part of what gives it a kind of mythic quality, even though it is a real place with real coordinates and real geology and real organisms living in it. It is the edge of the accessible world, the boundary between what we can routinely explore and what remains largely unknown, the place where our technology reaches its limits and where the cost of gathering information becomes high enough that we must choose carefully what questions to ask and what measurements to make. And in being at that boundary, the Challenger Deep reminds us that there are still places on Earth that resist easy knowledge, that remain mysterious, not because they are inherently unknowable, but because they are difficult to know, because reaching them and studying them requires patience and resources, and a willingness to invest in understanding for its own sake, without immediate practical return. The history of human engagement with the deep ocean is surprisingly short, measured not in millennia or centuries, but in decades, a time frame that barely registers against the age of the ocean itself or even against the span of human civilization. For most of human history, the ocean was understood only at its surface, as a barrier to be crossed or a resource to be harvested, and the depths below were inaccessible, unknowable, presumed to be empty, or inhabited by creatures too strange to imagine. The ancient Greeks believed the ocean to be shallow, a relatively thin layer of water overlying the solid earth, and this belief persisted into the modern era not because people were incurious, but because they had no way to measure depth beyond the reach of weighted lines, no technology that could sound the abyss and return information about what lay below. Early attempts to measure ocean depth using hemp ropes with lead weights attached reached perhaps a few hundred meters before the rope became too heavy to manage or broke under its own weight, and these shallow soundings reinforced the impression that the ocean floor was not far below the surface, that the depths were limited, that the solid earth beneath the water was not fundamentally different from the solid earth beneath the continents. It was only in the 19th century, with the development of stronger cables and mechanical winches, and the motivation provided by the desire to lay telegraph cables across the Atlantic, that systematic deep ocean sounding became possible, and the results were surprising. The Atlantic was deeper than expected, with soundings regularly exceeding 3,000 meters, and in some places reaching 4,000 meters or more, depths that required hours to measure because the weighted line had to be lowered slowly to avoid breaking and then hauled back up even more slowly. And each sounding was an event, a deliberate effort that consumed time and resources and gave only a single data point, a depth at a single location that had to be interpolated with depths from other locations to build any kind of map. The HMS Challenger expedition of the 1870s, which spent 3.5 years sailing around the world's oceans and conducting soundings and collecting samples and documenting the biology and chemistry and geology of the deep sea, discovered depths exceeding 8,000 meters in what is now called the Challenger Deep, though the measurements were imprecise by modern standards and the exact location of the deepest point was uncertain, and it would be decades before the full extent of the Mariana Trench was mapped, and the record depth confirmed. What these early soundings revealed was not just that the ocean was deep, but that it was variable, that the seafloor was not a flat plain, but a landscape with features as dramatic as anything on land, with ridges and valleys and canyons and mountains, with topography that was shaped by geological processes that were poorly understood at the time, but that clearly operated on scales that were vast and powerful. The mid-ocean ridges, the underwater mountain ranges that run through the center of every ocean basin, were discovered through systematic sounding in the early 20th century, and their existence posed questions about how underwater mountains could form and why they were located where they were. Questions that were not answered until the 1960s, when the theory of plate tectonics provided a framework for understanding the creation of new ocean floor at ridges and the destruction of old ocean floor at trenches. The trenches themselves, the deep, narrow depressions that mark subduction zones, were among the last major features to be mapped, simply because they were the deepest and therefore the most difficult to sound, and their significance was not understood until the geological context became clear. But mapping the topography of the ocean floor, measuring its depths and documenting its features, is not the same as understanding what those depths mean, not the same as grasping the conditions that exist in the deep, or the life that inhabits it, or the processes that operate there. For that, you need more than soundings. You need samples of water and sediment and organisms. You need measurements of temperature and pressure and chemistry. You need observations of what actually exists at depth, not just inferences based on surface conditions. And acquiring those samples and measurements requires technology that can function under pressure, instruments that can survive the descent and the time at depth and the ascent, and for most of the history of oceanography, that technology did not exist, or existed only in primitive forms that were unreliable and limited in what they could measure. Bottles for collecting water samples from depth were developed in the late 19th century, mechanical devices that could be lowered on cables and triggered to close at specific depths, trapping water that could be brought back to the surface and analyzed. And these bottles revealed that deep water was cold and dense and poor in oxygen compared to surface water, but they gave only chemical information, no sense of what the water looked like or what lived in it or how it moved. Cameras were adapted for underwater use in the early 20th century, housed in pressure-resistant cases and lowered on cables with lights to illuminate the seafloor, and the photographs they brought back were revelations, showing that life existed at depths where the pressure was immense and the temperature was near freezing and the light was absent, showing organisms that were strange in form but recognizable in function, fish and crustaceans and worms and other creatures that looked alien, but that were clearly adapted to their environment and thriving within it. These early photographs were blurry and difficult to interpret, limited by the technology of the time and by the difficulty of positioning a camera precisely on a cable thousands of meters long, but they proved that the deep ocean was not a lifeless void, that it supported ecosystems as complex and diverse as those at the surface, just operating under different constraints and with different energy sources. The development of submersibles in the mid-20th century, vehicles that could carry humans or instruments to depth and maneuver once they arrived, transformed deep ocean research by allowing scientists to see the seafloor directly, to observe organisms in their natural habitat, to collect samples with precision rather than by blind dredging, to measure conditions in situ rather than inferring them from samples brought to the surface. But submersibles were expensive and rare, and even today there are only a handful of vehicles capable of reaching the deepest parts of the ocean, and the time they can spend at depth is limited by power supplies and life support systems and the psychological endurance of the crew. Most of what we know about the deep ocean comes not from direct observation but from remote sensing, from instruments lowered on cables or deployed autonomously, from acoustic mapping and seismic surveys and chemical analysis of water and sediment samples, from piecing together indirect evidence into models and theories that explain what we observe but that are always provisional, always subject to revision as new data becomes available. And so the Challenger Deep remains, even after more than a century of study, a place that is known primarily through fragments, through brief visits and limited observations, through measurements that capture moments but not processes, snapshots but not continuous records. We know its depth to within a few meters. We know its temperature and salinity and pressure. We know some of the organisms that live there and some of the chemistry that occurs there, but we do not know it the way we know places on land that can be visited regularly and studied over long periods. Places where we can set up permanent stations and monitor conditions continuously and conduct experiments and build a detailed understanding through sustained observation. The deep ocean is too difficult to access for that kind of sustained presence, and so it remains in many ways as remote and mysterious as it was a century ago, better understood in some ways but still fundamentally alien, still a place at the edge of what we can know directly. The act of descending to the Challenger Deep, of traveling those 11 kilometers through water that grows steadily darker and colder and more pressurized, is an act that requires confronting human limits in a way that few other endeavors do. You cannot simply walk to the bottom of the ocean. You cannot swim there or dive there with any equipment that currently exists or is likely to exist in the foreseeable future. You cannot go there casually or spontaneously, or without extensive preparation and support, and the acceptance of risks that are significant even with the best technology available. You can only go there inside a vessel, protected from the environment by walls of metal or composite material that must be thick enough to withstand pressures that would collapse anything weaker, and even then, you are not really there in the sense of being present in the environment, of touching it or breathing it or experiencing it directly. You are inside a bubble, a small volume of air at surface pressure, looking out through viewports at a world that exists just centimeters away, but that might as well be on another planet for all the accessibility it has. The pressure differential across those viewports, across those few centimeters of transparent material, is more than 1,000 atmospheres, a force that is constantly trying to push the viewport inward, to collapse it, to equalize the pressure by destroying the boundary between inside and outside. This mediation, this necessary separation between human presence and the deep ocean environment, creates a particular kind of experience, one in which you are simultaneously in a place and isolated from it, able to see it but not to touch it, able to measure it but not to feel it except through instruments that translate pressure and temperature into numbers on displays. It is an experience of observation rather than participation, of witnessing rather than inhabiting, and it carries with it a sense of humility that comes from recognizing how small and fragile human bodies are in the context of an environment that is indifferent to our presence, that operates according to physical laws that do not accommodate our needs or preferences, that simply is regardless of whether we are there to observe it or not. The deep ocean does not care if we understand it. It does not care if we visit it or study it or marvel at its extremes. It exists in its own right, following its own patterns, sustaining its own ecosystems, participating in planetary cycles that were operating long before humans evolved and that will continue long after we are gone. This indifference is not hostile. It is simply neutral, the neutrality of a natural system that has no awareness of observers, no capacity for concern or consideration. The pressure at the bottom of the Challenger Deep is what it is because of the weight of water above it, not because of any intent or purpose. The cold is what it is because of the way water circulates through the ocean and because of the thermal properties of seawater at depth. The darkness is what it is because light cannot penetrate thousands of meters of water. These are consequences of physics and chemistry, outcomes determined by the properties of matter and energy, and they would be exactly the same whether humans had ever evolved to contemplate them or not. And yet there is something profound in the act of contemplation, in the effort we make to understand these places, to measure them and map them and document the life that exists within them, because that effort reflects something fundamental about human nature. A curiosity that extends beyond immediate practical needs, a desire to know what lies at the extremes, to answer questions not because the answers will make us richer or safer or more powerful, but simply because we want to know, because the questions exist and we are capable of asking them. The history of deep ocean exploration is, in many ways, a history of human ingenuity applied to the problem of overcoming environmental barriers, of finding ways to extend our senses and our presence into places that are hostile to biological life as we know it. Every instrument that has been sent to the deep, every submersible that has descended to Hadal depths, every remotely operated vehicle that has crawled across the floor of a trench represents a solution to the problem of how to function under pressure, how to maintain structural integrity when forces are trying to crush you, how to generate power and control movement and collect data in an environment where every action requires more energy than it would at the surface because the medium is denser and more resistant. These are not trivial problems, and the solutions are not simple, and the fact that we have solved them well enough to reach the Challenger deep and return with information is a testament to human technical capability, to our ability to engineer systems that can operate outside the narrow range of conditions that our bodies are adapted to. But alongside this testament to capability is a recognition of limitation, an acknowledgement that we can only reach these places with great difficulty and at great cost, that our presence there is temporary and fragile, that we are visitors in an environment that does not welcome us and that we leave behind as soon as we have gathered the information we came for. There is no permanent human presence in the deep ocean, no stations or habitats where people live and work for extended periods, no infrastructure that would allow routine access or sustained study. Every trip to the deep is an expedition, an event that requires planning and resources and carries risks, and the total number of hours that humans have spent in the deepest parts of the ocean is vanishingly small compared to the time we have spent in space or on mountains or in any other extreme environment that we have chosen to explore. This asymmetry is telling. It suggests that the deep ocean is, in some fundamental way, more difficult for us to access than space, more resistant to human presence than the vacuum beyond Earth's atmosphere. And this is true not because space is easier in any objective sense, but because the challenges are different. Because maintaining a pressure vessel against the crushing force of deep water requires different engineering than maintaining a pressure vessel against the vacuum of space, and because we have invested more resources and effort into space exploration than into deep ocean exploration, a choice that reflects our priorities and our curiosities and perhaps our biases about what counts as frontier and what counts as unknown. The deep ocean is a frontier, but it is a downward frontier, a frontier beneath rather than above, and perhaps this changes how we think about it, makes it seem less appealing or less significant than the outward frontier of space. We look up at the stars and feel drawn to them, feel a sense of wonder and possibility, feel that reaching them would represent some kind of transcendence or expansion of human capability. But when we look down into the ocean, when we contemplate the depths below us, the feeling is different, more sobering perhaps, more grounded in the physical reality of the planet we inhabit, less about reaching outward and more about understanding what is already here, what has always been here, what exists beneath the surface we take for granted. The Challenger Deep is not light years away. It is 11 kilometers below sea level, closer than most of the places we travel to regularly, but it is almost as inaccessible as the planets of other solar systems, separated from us not by distance in the conventional sense, but by depth, by pressure, by the sheer difficulty of functioning in an environment where every physical property is different from the environment we are adapted to. And yet the deep ocean is part of our planet, part of the system that sustains life on Earth, part of the cycles of water and carbon and heat that regulate climate and distribute nutrients and connect the surface world to the interior of the planet. Understanding the deep ocean is not a luxury or a curiosity. It is part of understanding Earth as a whole, part of grasping how the planet functions as an integrated system, how the processes that happen in the deep influence the processes that happen at the surface, how the circulation of water through the ocean basins affects global climate, how the chemistry of the deep influences the chemistry of the atmosphere, how the biology of the deep contributes to the total biodiversity of the planet. The Challenger Deep is an extreme, but it is not separate. It is connected, part of the whole, and exploring it and studying it is part of the larger project of understanding our home, of knowing the planet we live on with sufficient depth and detail that we can make informed decisions about how to interact with it, how to protect it, how to ensure that it remains habitable not just for us but for the countless other species that share it with us. There is something in the human mind that is drawn to edges, to boundaries, to the places where measurement reaches its limits, and records are set. We climb the highest mountains, not because there is anything at the summit that we need, but because the summit is there, because it represents a maximum, a point beyond which you cannot go higher without leaving the planet. We travel to the poles, not because they offer resources or strategic advantage, but because they are the ends of an axis, the points where the Earth's rotation intersects its surface, places that are extreme by definition, even if the landscape there is not fundamentally different from landscapes at other latitudes. And we seek out the deepest points in the ocean, the places where the seafloor reaches its maximum distance below sea level, not because those places are necessarily more interesting or more important than other parts of the deep ocean, but because they represent a limit, an extreme, a record that can be stated simply and understood immediately, even if the reality behind the number is difficult to grasp. The Challenger. Deep satisfies this attraction to extremes in a way that is particularly pure because its record is unambiguous. It is the deepest point on the solid surface of the Earth, the place where you cannot go any deeper without somehow penetrating through the seafloor itself. And this fact is measurable and verifiable and accepted by consensus among scientists who have studied the world's ocean trenches. There are no competing claims, no disputes about methodology or definitions, no questions about whether some other location might be deeper if measured differently. The Challenger Deep is simply and definitively the deepest place on the planet. And knowing this satisfies something in us that wants clarity, that wants the world to have a definite structure with identifiable limits, that wants to be able to point to a map and say, there, that is the extreme, that is as far as it goes in that direction. But records and extremes, for all their appeal, are ultimately abstractions, facts that exist in databases and reference books, but that do not change the fundamental nature of the places they describe. The Challenger Deep would be exactly what it is whether or not humans had identified it as the deepest point, whether or not we had measured its depth, or sent vehicles to explore it, or written its name on charts. Its depth is not a human creation. It is a geological fact, a consequence of plate tectonics and the subduction of the Pacific Plate beneath the Philippine Sea Plate, and it existed long before we knew about it, and will continue to exist long after we have stopped paying attention to it. The significance we assign to it, the way we think about it as a record or an achievement or a destination, is entirely human, entirely a product of our need to organize the world into categories and hierarchies, to identify what is biggest or smallest or deepest or highest, so that we can understand where we stand in relation to those extremes. And yet there is more to the Challenger Deep than its status as a record, more to it than the number that appears in textbooks and documentaries. There is the reality of the place itself, the actual physical environment, with its particular temperature and pressure and chemistry, the organisms that live there, and the sediment that covers the floor, and the slow geological processes that are constantly reshaping it. This reality exists independent of human knowledge or attention, and it is this reality that matters in the long term, not the record or the achievement of having visited it, but the ongoing existence of an ecosystem and a landscape that participate in planetary processes regardless of whether anyone is observing them. The Challenger Deep is not interesting solely because it is deep. It is interesting because it is a place, with its own character and its own patterns, with life that has adapted to conditions that seem impossible, and with geology that reveals something about how the Earth works at its most fundamental level. Understanding this distinction between the abstract significance of an extreme and the concrete reality of a place requires a shift in perspective, a move away from thinking about the Challenger Deep as a point on a map or a number in a database, and toward thinking about it as a location in the physical world, a site where specific processes occur and where specific organisms live and die and reproduce. This shift does not diminish the significance of the depth measurement, does not make the record any less impressive, but it does contextualize it, places it within a larger framework of understanding that includes not just the measurement, but what the measurement represents, not just the fact of depth, but the consequences of depth, for everything that exists at that location. Depth is not just a vertical distance. It is a set of conditions, an environment defined by pressure and temperature, and light availability and food supply, and those conditions determine what can live there and how it can live, and what adaptations are necessary for survival. The organisms at the bottom of the Challenger Deep do not experience depth as a number. They experience it as pressure, as cold, as darkness, as scarcity of food, as a set of physical constraints that shape every aspect of their existence. For them, the depth is not an abstraction, but a lived reality, something that affects their cells and their metabolism and their behavior every moment of their lives. And in this sense, the deepest point on Earth is not special to them. It is simply their environment, the place where they exist, no more remarkable to them than the surface world is remarkable to us. We do not think of ourselves as living at a depth of 0 meters or at 1 atmosphere of pressure. We think of ourselves as simply living, as existing in the normal environment that our species is adapted to, and it is only when we encounter other environments, when we climb mountains or dive underwater or travel to space, that we become aware of the specific conditions that define our usual habitat. The same is true for deep-sea organisms. They are adapted to their depth, and it is the surface that would be extreme for them, that would represent an environment where they could not survive, where the pressure is too low and the temperature too variable and the light too bright. This relativity of extremes is worth contemplating because it reminds us that our perspective is not universal, that what seems extreme or unusual to us is normal to organisms that have evolved in those conditions, and that the labels we apply, the records we keep, the significance we assign to particular places are all filtered through our particular experience and our particular limitations. The Challenger Deep is the deepest point on Earth from a human perspective, measured from sea level, which is itself a human reference point, but from the perspective of the planet as a whole, it is simply a depression in the seafloor, one feature among many in a topography that includes mountains and ridges and plains and trenches, all of which are equally real and equally significant in terms of the geology that created them and the ecosystems that inhabit them. The fact that we have chosen to focus on the deepest point to assign its special significance tells us something about ourselves, about our fascination with extremes and records, but it does not necessarily tell us anything fundamental about the ocean or the planet. And yet, even acknowledging this relativity, even recognizing that our interest in the Challenger Deep is partly a projection of our own values and curiosities, there remains something genuinely profound about the place, something that justifies the attention we give it. It is not just that it is deep, though the depth is impressive. It is that the depth represents a synthesis of forces and processes that operate throughout the planet, that the trench exists because of plate tectonics and because of the way the Earth's crust is structured, and because of the interplay between solid rock and molten mantle and the slow convection that drives everything. And understanding that synthesis, grasping how all these elements come together to create a place like the Challenger Deep, is part of understanding how Earth works as a system. The depth is a consequence, an outcome, but it is an outcome that reveals causes, that points back toward fundamental processes, and in studying the deepest point, we are also studying the mechanisms that shape the planet's surface, that create mountains and valleys and ocean basins, that recycle crust and redistribute materials and maintain the dynamic equilibrium that allows life to persist on a planet that is constantly changing. There is a particular stillness that settles over empty places late at night, when the air has cooled and the wind has dropped to almost nothing, and the darkness feels complete, not because it is hostile, but because it is simply the absence of light, a neutral state that requires no explanation and offers no commentary. In such moments, standing on solid ground with the vast sky above and the silent earth below, it is natural to think about what lies beneath, about the layers of rock and soil that extend downward from where you stand, about the roots of mountains and the foundations of continents and the deep places that exist beyond sight and beyond reach. We think of depth as something that begins where we are standing and extends downward into the familiar earth, and this intuition, this assumption that the deepest parts of the world must lie beneath the land we walk on, feels reasonable because it is grounded in our daily experience, in the fact that we are terrestrial creatures for whom depth means digging or descending or burrowing into the ground. But the planet does not organize itself according to human intuition, and the truth about depth, The answer to where the surface of the Earth reaches its lowest point is not where most of us would think to look. It is not beneath continents or inside mountains or at the bottom of valleys carved through ancient rock. It is beneath the ocean, hidden under thousands of meters of water, in a place that most people will never see, and that exists for most of us only as knowledge, as a fact learned and accepted but not experienced, not felt in the way we feel the ground beneath our feet or the air against our skin. The Challenger. Deep, the deepest point on the solid surface of the planet, lies in the darkness and cold and pressure of the Western Pacific, 11 kilometers below sea level, a distance that is difficult to comprehend and even more difficult to reach, a place that represents the true extreme of depth on Earth. And yet, for all that has been said about this place, for all the measurements and observations and expeditions that have been conducted there, the Challenger Deep remains in essential ways unknown. We know its location and its depth and something of the conditions that prevail there. We know that life exists at the bottom, that organisms have adapted to pressures that would crush most living things, that the trench floor is not empty, but inhabited by creatures that move slowly through the sediment and feed on whatever organic matter falls from the world above. We know that the trench is not permanent, that it is being created by the subduction of one tectonic plate beneath another, and that it will eventually be destroyed or replaced by some other feature as the configuration of continents and ocean basins continues to shift. But knowing these things is not the same as understanding the place in any complete or final sense, not the same as grasping what it means to exist in that environment, or how it feels to be so far removed from the surface world, so deeply isolated in darkness and pressure and cold that has no variation and no end. There is a limit to what can be known about places we cannot inhabit, places we can only visit briefly and with great difficulty, places that do not accommodate human presence and that remain fundamentally alien no matter how much we study them. The Challenger Deep exists at that limit, not because it is unknowable in principle, but because knowing it fully would require a kind of sustained engagement that is not possible with current technology and may never be possible, a presence that is continuous rather than episodic, a familiarity that comes from living in a place rather than merely passing through it. And perhaps this is as it should be. Perhaps there is value in having places on Earth that remain beyond easy knowledge, that resist casual exploration, that require humility and patience, and a recognition that not everything can be mastered or possessed or fully understood. The wind moves across empty places, carrying nothing, touching no one, and the ground beneath us feels solid and permanent, even though we know it is part of a surface that is constantly changing, constantly being reshaped by forces that operate on timescales we can barely imagine. And far below, deeper than the mountains are tall, deeper than light can penetrate or warmth can reach, the ocean floor stretches away into distances that are measured in thousands of kilometers and depths that are measured in numbers that require comparison to make sense of. The deepest part of the planet is not on land, and this inversion of expectation, this quiet correction of intuition, is worth carrying with you, worth returning to when the mind wanders toward questions about where things begin and end, about what lies at the edges of the known world, about the vastness that exists beneath the familiar surfaces we take for granted. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.